So, in the previous lecture we saw the general solution of the wave equation u t t minus c square u x x equal to 0 is given by u x t equal to f of x plus c t plus g of x minus c t. So, this actually represents a wave moving forward direction. Okay. Maybe later I will show you some pictures. So, you can yourself take some simple function and try to draw these functions for different values of c and observe this phenomenon moving forward, and this is moving properly. So, backward. So, in general the solution of the wave equation is a combination of forward moving profile and backward moving profile, and now we will determine f and g given two initial conditions. So, let me just initial conditions. So, u x 0 u 0 x and u t x 0 equal to u 1 x. So, here we have taken t equal to 0 as the initial time. So, the first condition represents the initial profile of the string, for example, and the second condition represents the initial velocity in the string. Okay. So, now we will see how these initial conditions help us to determine f and g in the general solution. So, if you plug in these initial conditions in the general solution, we see that so plug in the general solution. So, you get u 0 x, I put t equal to 0 here, you see that. So, f of x plus g of x, and now you take time derivative of the general solution and again put t equal to 0. So, left hand side you get u 1 of x, and when I differentiate with respect to time there, so I get c f prime x minus c g prime x, because there is minus c there. So, that is why I am getting minus c. Okay. So, these are more linear equations, but only thing is now f and g are not numbers, they are functions, but we can easily determine them. So, you integrate the second equation. Okay. So, you integrate it. get C f x minus C g x is equal to integral 0 to x u1, let me use the variable j dj plus some constant, where k is a constant of integration. So, we will see that is irrelevant. We will see that. So, okay. So, now we have one equation with f x plus g x and another one essentially f x minus g x. So, we can easily solve them. So, I will write the formula here. So, we get f of x is equal to half u 0 x plus 1 by 2 c 0 to x u 1 j d j. Okay, do not confuse that j with characteristic variable. This is just a dummy variable for integration k by 2, and g of x half u 0 x minus 1 by 2 c 0 to x, same thing, minus k by 2. So, this expressions for f and g will be using many times in the future also. So, just remember how they are derived. Okay, now we go back and to the general formula and now find out the solution for the wave equation. So, therefore, u of x t, so we have that f of x plus c t plus g of x minus c t. So, now I have expressions for f of x and g of x. So, I just have to replace x by x plus c t and x by x minus c t. So, I get half u 0 x plus c t plus 1 by 2 c 0 to integral 0 to x plus c t u 1 j d j. K is a constant, so that will not change. So, just k by 2. This is for f of x plus c t, and similarly for g of x minus c t. So, I have half u 0 x minus c t minus 1 by 2 c integral 0 to x minus c t u 1 j d j minus k by 2. Okay. So, you immediately see that constant of integration has no role to play. So, that will just vanish, and so we will simplify this half u 0 x plus c t plus u 0 x minus c t, combining these two terms and combining the integral. So, we have 1 by 2 c. So, 0 to x minus C t, we will write it as minus x minus C t to 0 and combine it. So, we get x minus C t to x plus C t u 1 j. Okay, so, let me write that. Okay. So, this is called D'Alembert's formula. So, remember it. So, because we will be using it throughout the discussion on one dimensional wave equation. So, let us analyze this formula a little bit. Okay. So, now we discuss two concepts. One is domain of dependence and another concept range of influence, and there is also a domain of determinacy that will come to next a little later, range of influence. Okay. So, what are these? So, again let me draw the picture x, and this is t. Okay. So, we want to determine the solution. So, let me write that as a theorem maybe. Okay. Let me write. Okay. The initial value problem IVP are also called Cauchy problem. UTT, so let me write it, UXX so this is in the region T positive and X is in R, and we are given the initial profile U1x, again x is in R. Okay. So, the equation and the condition, the two initial conditions in this case, and this is referred to as Cauchy problem, has this has the solution given by the D'Alembert's formula. Okay, so, let me not repeat it. So, just so a word about the concept of solution again. So, this we have discussed earlier also. So, here we are seeking C2 solution to the wave equation satisfying the given initial conditions. Okay. So, for that we do require, if you look at the D'Alembert's formula, we require u0 a C2 function, and since in the D'Alembert's formula u1 gets integrated. So, for that we only need C1. Okay. So, then if u0 is a C2 function and u1 is a C1 function, then the wave equation has the solution given by D'Alembert's formula, hence it is unique. So, here we do not have to prove the uniqueness separately, because we are deriving a formula for the solution, but in many other cases that uniqueness has to be proved separately, that I will make some remarks. Okay. So, if you look at the D'Alembert's formula, so let me just remove this thing and just put a T here. Okay. So, we are trying to find the solution at a point x t. So, if you look at the D'Alembert's formula, it depends on the initial conditions. Okay, this is why. Okay. So, this is, if that is x t, this will be x plus c t, and this is x minus c t. Okay. So, D'Alembert's formula tells us that the value of the solution at the point x t, t is positive, depends only on the values of the initial values only in this interval, only in this interval, that is important, okay. Nothing else. So, u0 x plus c t, u0 x minus c t, and u1 is integrated over this interval. Okay. So, this is referred to as this interval, domain of dependence. So, in other words, the value of the solution at the point x t depends on the values of the initial data only in this interval. So, that is an so that is how the finite speed of propagation comes into picture. So, what is range of influence? So, that is another so, we take a point y on the initial line t equal to 0, that is x axis or t equal to 0. And now, we would like to see the value of the initial data at this point, how it influences the solution for a positive t. So, you take a positive t, fix it. So, this can again you look at the D'Alembert's formula, you see that. So, this goes there, this goes here. So, So, this is y minus C t, y plus C t. So, the let me go back to the color. The values of the initial u0 and u1 at y, that is on the initial line, will influence the value u x t So, t is positive only if x belongs to y minus C t and y plus C t. Okay. So, as you change t, of course, that interval gets expanded. Okay. This so, this is referred to as range of influence. Okay. So, these are two important concepts, and these are also used in devising numerical schemes for solving the wave equation. When you want to solve numerically range of influence of all. Okay. So, these are two important concepts. Okay. And now, if you combine these two, so that is what we next get. So, instead of taking one single point, you take an interval. So, this another concept. So, instead of taking one point on the domain of determinacy, so and again on the initial line t equal to 0, now you take an interval a b. So, now you determine the range of influence of all these points in this interval, and what you get is this. So, at any time this will become the domain of determinacy. So, this is domain of determinacy. So, you take the union of the range of influence of all the points in this interval. Okay. So, that is the concept of domain of determinacy. So, before we go further, just let me make one comment. So, again let me stress that okay. So, in order to get a C2 solution of the wave equation, we need to assume that u0 is a C2 function and u1 is a C1 function. What happens if I relax this condition? Okay. So, let us take some examples and see what we get. Of course, we do not expect a C2 solution, but we will see what happens. Okay. What happens? So, that is the question. What happens if u0 or u1 or both do not have required smoothness? So, this is an important concept in modern theory. So, just want to make a remark, we are not going smoothness. So, let me take a simple example. So, u0x has a jump discontinuity, sorry for that, -1 if x is less than 0 plus 1. So, you see that u0 has simple jump discontinuity at x equal to 0, and I am taking u1 for simplicity. You can work out many problems. So, let me explain the solution. Graphically. So, that is much easier. Okay. So, this again x and t okay. So, I have here u0 equal to -1 and u0 equal to +1. So, we expect some difficulty at this origin. So, let us draw the characteristics to that. So, this is x equal to C t characteristic. So, let me draw this another one x equal to minus C t. They are straight lines though they do not look straight lines here, but okay, that is I am writing that. So, if you take any point here x t, what is the relation between x and t in this case? So, it lies below the line x equal to minus C t. So, x is less than minus C t, and if you look at the D'Alembert's formula, okay, it is domain of dependence. So, that is why it is important, very important. Okay. So, its domain of dependence lies entirely in the negative x axis, that is very important. Okay. If you take any point below this line, its domain of dependence lies in the negative x axis, where u0 is -1 and u1 is identically 0. So, you get u of x t, look at the D'Alembert's formula, you simply get -1. Okay. So, this region you get u of x t. So, let me write it. Okay. For all the points below this characteristic x equal to minus C t, and similarly if you take any point below the characteristic x plus C t, and again its domain of dependence lies entirely on the positive x axis. So, you get again u of x t is equal to +1, because u0 is 1 here. Okay. So, just plug in the D'Alembert's formula and you get that. But if you take any point between these two characteristics, you take any x t here. Okay. So, its domain of dependence now, one end point lies in the negative x axis and another one lies on the positive x axis. Okay. Again if you plug in the D'Alembert's formula, you see that u is, it is -1 +1 because u 1 is anyhow 0. So, you get u is 0 here. Okay. So, u is minus 1 here, in this region u is 0, okay, and u is 1 again. Okay. So, what we see here is that in 3 different regions. So, this separated by 2 characteristics, x equal to minus C t and x equal to C t. So, u is C 2, in fact, it is as smooth as u 0, they are C infinity here. So, it is also C infinity, no problem there, it's constant functions, and you see it has jump discontinuity across this characteristic and it has jump discontinuity. Okay. So, the jump discontinuity in the initial value at one point now propagates along these characteristics emanating from that point, not any other characteristic, only those 2 characteristics emanating from that origin. Origin is the point of singularity of the initial conditions. So, this is termed as propagation of singularities, and is an important topic and nowadays used in many inverse problems, okay, but it is very difficult topic. So, those who are interested can look into literature to have a glimpse of what this propagation of singularities for general hyperbolic equations. So, this is the simplest case, we have D'Alembert's solution. So, we can see where the solution has discontinuities. So, it is important to note that the solution has discontinuity only along the characteristics emanating from that one point where the initial condition has jump discontinuity. Okay. So, that is I will stop here, and next time I will make little more elaboration on this propagation of singularities, and then we will move on to other topics in one dimensional wave equation. Thank you.